Hello, everyone. Welcome to the first Learning at Tomography session. And the first talk will be by Enrique and Elias here about unitary Schur sampling with application in state tomography.
Hello, and welcome to the talk about unitary Schur sampling and state tomography. I have a mic here, I think. This is in collaboration with Yanglin, Laura, and Marco. Marco is also on the conference if you want to talk to him. Enrique and me are here. And we're going to talk today about two papers that we've published. The first one is about unitary Schur sampling and the motivation behind it and an efficient, memory-efficient algorithm for it. And the second one is about the application of unitary Schur sampling in state tomography, which is also why this talk is split in two. I will first talk about unitary Schur sampling, and then Enrique will tell you a bit more about the application in state tomography. OK, let's get right to it. What is unitary Schur sampling? Why should I care about it? I will tell you now. In quantum information theory, we often have the case that we have some input state on many different registers. This is very general. For example, row 1 tends to row 2, and so on until row n. And in some problems, we actually have the symmetry that we don't care about the order of these states. And examples are given here as spectrum estimation, state tomography, cloning. And there especially, we just get n copies of the same state. So we don't care in which order kind of these states are arranged. And this makes us want to use the symmetry to kind of simplify the problem. And to this end, we want to understand the action of the permutation group Sn on this vector space. And a very nice thing, or a very useful tool for that, is Schur-Weil duality, which maybe some of you have already heard. It's a very strong tool in quantum information theory, because it tells us that the vector space CD to the n is equivalent to this direct sum of, they're called isotypic subspaces, labeled by these lambda. These lambda, maybe some of you know as Young diagrams. They're partitions of n. And what Schur-Weil duality tells us is that the action of the permutation group is diagonalized. Because if I act on the left-hand side of this equation with some permutation, I permute kind of the registers. On the right-hand side, I will actually just act block diagonally. I will only act within each of these blocks, only on the p lambda register. And I will leave the q lambda register invariant. So all the information about permutations is somehow contained in the p lambda register. And we call this transformation the Schur transform, this u sh with the n on top of it. Yes, and this is what we're going to use. And let's apply it to our state, rho to the tensor n. We can now use Schur's lemma and the Schur transform to say that rho to the tensor n actually has this form. That means it's a direct sum over these lambdas, over the maximally mixed state on the permutation register, and some state on the unitary register. And this really makes sense. We don't have any permutation information about the state, because its maximum is symmetrized. Like, we have no idea about in which order they arrived. And if we look at this from an information point of view, we see that there's no entanglement between the blocks. So this lambda structure, this direct sum, is purely classical information. There's no information at all on the permutation register, because it's the maximally mixed state. And all the information, all the quantum information, is condensed on the unitary register. So now, I have to say, this holds for any symmetric input state. I'm just using rho to the tensor n here because it's didactically a bit easier to. It's a bit more concrete example. But now we can take this. We can say, OK, this is our state. We can measure the label lambda, because as I said before, this is just classical information. And we can then dump the permutation register, because there was no information on it anyways. And this is what we need in our quantum algorithm. And this is a primitive for any task that has this symmetry. Because as I just showed, this is all the information you need for these tasks. And we call this primitive unitary Schur sampling. And it is the task equivalent to performing the Schur transform, measuring lambda, tracing out the permutation irrep, and then returning the state on Q lambda. And a very important, minor but important detail here is it's equivalent. That means while I can do unitary Schur sampling like this, doesn't mean that it's the best way to do it. And let's get right to it. Let's look at the kind of naive way to do unitary Schur sampling. We take all our input states, we take the Schur transform, and then we measure lambda. We discard the permutation register here on top, and we keep the blue register, the unitary register. And let's look a bit closer at this box in the middle. The implementation from Bacon, Chuang, and Harrow, which is, by the way, a very nice kind of result, they showed that you can perform the Schur transform by performing this ladder of Klipsch-Gordon transforms, which always takes two irreps, two unitary irreps, and gives you a new irrep decomposition. So you take two irreps on the left, and you get one irrep out. You can see this at the start. You just take two states, because CD is an irrep, the fundamental irrep, and then you get row lambda out. You also get the label of the new irrep out, this lambda 1. And the lambda 0, or in this case, the control lambda, just tells you in which irrep you started. And kind of you perform this diagonally, you one after another add all your input states row, and in the end, when you have added your last input state, what you are left with is some state on a unitary irrep, row Q lambda, which is the unitary irrep, some label lambda. The last label lambda will tell you which irrep or which isotypic subspace you're on. And all the previous labels, this is kind of a nice thing that Harrow showed in his thesis, all the previous labels actually form a basis of the permutation subspace. So you kept them all, and suddenly, for free, you get this basis for the permutation subspace. But now we remembered that we actually don't care about this red part. We're going to throw it away anyways. So kind of dragging along all of this top right corner is not really nice. And also in the bottom left, we only need these rows when we actually perform the corresponding Klipsch-Gordon transform. We don't need them before. So we drag a lot of unnecessary memory this way. So what we can do is just perform this operation. And kind of on the top, we just discard the registers. On the bottom, we assume that we get streaming access to the rows. So we have someone else, maybe some company that produces these states for us, or some experiment where you produce these states one after another. And we only tell them, OK, now we're ready to get the next state. Now get the next state. So we don't need to store all of them at once. And if you look at the memory, you see indeed that before I had to store this whole Hilbert space, CD to the tensor n. And this takes memory n log d. Now I have to store these, like the previous label, the new label, the state row, and the state on the irrep. And basically only the state on the irrep matters. The other stuff is easy to store. And this irrep, kind of, there are these upper bounds of the dimension. And after all is said and done, the memory of this irrep is dr log n. So suddenly we're logarithmic in n. And if you watch the talks, the plenary talks today, this is a bit akin to the fact that types have, like, they scale differently. The number of different types scale differently than the number of different strings. Just a side note. Yes. And this brings us to our results. We get exponential memory savings in n for performing unitary Schur sampling when compared to the naive implementation via Schur transform. We also, by doing this, at the side, we investigated the Klipsch-Gordon transforms as proposed by Harrow and the others. And we noticed that their time complexity can actually be improved by this factor r cubed over d cubed, where r is the rank of the input state. And reduced rank promises are very common in state tomography and similar problems. And this reduction in time complexity actually also applies to the Schur transform. And finally, we also get unitary Schur sampling for mixed Schur-Weyl duality, which is a more general form of Schur-Weyl duality, where you also have the dual action of the unitary group. And with that, I'll let my colleague take over.
Thank you, Elias, for the objectively wonderful talk. As promised, I will now discuss one of the applications for unitary Schur sampling in quantum state tomography. So first, a little bit to motivate what is state tomography. So state tomography, in general, is the task of producing a classical estimation of an unknown state rho when you're given access to n IID copies of the state rho. The more general way algorithm for quantum state tomography is as follows. During every round of the algorithm, you will receive quantum state, say round I. You will then operate, you will add that state to some existing quantum memory that you have. And based on some maybe classical state information that you have from previous rounds, you will perform sort of operation on this state that you receive, and then carry on with further quantum register and classical state information for subsequent rounds. We say that this is a very general model for quantum state tomography algorithm because you'll notice that this kind of setup also includes quantum state tomography algorithms that are fully coherent, where you're allowed to store all copies until the very end, as well as algorithms that only measure one copy at a time, either adaptively or non-adaptively. In general, the three kind of figures of merit that we're interested in a quantum state tomography algorithm are first and foremost the sample complexity, which is the minimum number of copies that you need to characterize the state rho to some desired accuracy. Then the memory complexity, which is basically the maximum size of the quantum register that you need to have at any point during your execution of the algorithm. And lastly, the time complexity, which is obviously the amount of gates that you need through an entire execution of your state tomography algorithm. So formally, quantum state tomography, given a state rho, you want to produce an estimate rho hat, which is ensured to be close in some sort of measure. In this case, for didactic purposes, we're using the trace distance. So tomography algorithm, you want to ensure that rho, the unknown state, is close to rho hat with some probability. We remark at this point that there are other measures that you can use. It is also common to see the infidelity between rho and rho hat. And we also use a condition for known as the probably approximately correct condition, which is certifying that you're close in trace distance or infidelity with a certain probability. But there's also different conditions that you can use, like second moment of distance. In fact, in this work, we also show that they're equivalent, second moment of distance and probably approximately correct. So the kind of goals towards efficient state tomography are obtaining an algorithm that is sample optimal, as well as memory and time efficient. So as promised, this is going to be an application of the unitary Schur sampling. And again, this is because of the nature of state tomography. You can receive the unknown state rho in a streaming/sequential manner. We want to take advantage of this to have an efficient algorithm. So right, the first step in most state tomography algorithms is to employ the kind of symmetry that you have in the input states. So as before, the first thing you want to do is apply the Schur transform, and this kind of decomposes the state rho tensor n into this isotypic decomposition. The next step in the known sample optimal algorithms is to then perform a continuous POVM on the unitary register part of your entire input state. So this continuous POVM has elements as given there in the second box. Essentially, you have a POVM element for each random unitary and for each partition lambda that appears on the isotypic decomposition. When all is said and done, your POVM will return a unitary U and Young label lambda. And then your output of the tomography algorithm is going to be that state rho hat, which is going to be U times a diagonal matrix with diagonal elements equal to the partition that is also normalized times this U dagger. And it is known that this state rho hat is going to be close in trace distance to the original state. It is known that this algorithm is sample optimal with upper and lower bounds as given in the green box. And our task is to minimize the memory complexity of this sample optimal algorithm. So the first obvious step is to perform the unitary Schur sampling that Elias was talking about. Again, this is a streaming algorithm that allows you to process a single copy of row as it is received. And ultimately, when all is said and done, the output of this unitary Schur sampling is going to give you a state which is row in the unitary register given by partition lambda. Okay? And this happens with memory and time complexity as given on the two bottom boxes. The next step, the hard step, is to somehow discretize the continuous P of M to be able to recreate the state row hat. The continuous P of M, as I mentioned before, is going to be it's going to have P of M elements given by Haar random unitaries U, and for each lambda. The n to the minus 1 is simply just a normalization factor. The obvious choice then for the discrete P of M is to choose some set of unitaries and then just have the same P of M elements, but only over that set of unitaries. Of course, this is going to induce some sort of error penalty given by this X residual. Of course, what this means is that whenever you apply this P of M, you're going to have some error probability, namely the one that you end, the one where you end up in the X-res domain. But we show in our work that this is actually exponentially suppressible, so it's not really a problem. So then the next task is kind of figuring out, okay, what set or what subset of unitaries do we want? So after some investigation, we found that it suffices to take some Haar random set, okay? And we found through some operator value Chernoff inequalities that in fact you need, that it suffices to sample Haar random unitaries up until your set U is of that size in the screen. Forming up this P of M, this discrete P of M was the kind of technical crux of the paper. But yes, we show that it exists. Using this discrete P of M, we're able to show that the estimate, again, U times the lambda bar diagonal matrix times the U dagger, actually satisfies the trace distance condition that we desire of a state tomography algorithm. And we are able to do this with memory complexity as given on the left box. This you can prove basically via Neymark and Solovay-Kitaev theorems. And essentially, the bottleneck for the memory complexity of this algorithm is the memory required to apply the discrete P of M, not the unitary Schur sampling part. So yeah, eventually we get a memory complexity that is linear in D, the dimension of the qubits, as well as R, which is the rank of the states. And most importantly, we obtain an exponential advantage in the error. Before, in the sample optimal algorithms, the memory was also dependent on 1 over epsilon, but we are able to delegate that to inside the log. The time complexity we're also able to calculate via the Solovay-Kitaev theorem. It's not very optimal. It's still better than for a continuous P of M over the Haar measure, but it's still to be seen for future work. So I guess as comparison to previous work, of course, it's a bit of a hard comparison because our algorithm we're assuming is quote-unquote coherent. We are able to apply a measurement on the equivalent of what you get after you perform unitary Schur sampling on all rounds. We obtain optimal sample complexity, similar to the fully coherent algorithms of O'Donnell, Harrow, etc. And again, with an exponential memory saving in the error. Then we also compare it with some T-coherent quantum state tomography algorithm, which I believe will be mentioned in some talk at some point. In essence, this T-coherent algorithm allows you to store T copies of the input states and then only measure T at a time. And then there's also obviously the single copy state tomography algorithms, in which you're only allowed to measure 1 copy at a time, adaptively or non adaptively. Of course, we also obtain similar results for the infidelity. In this talk, I focused on trace distance, but all our results also applied to the infidelity accuracy measure. And as an extra added result, we also join the 2 conditions for state tomography, which is the probably approximately correct, as well as the second moment of distance. Yeah, so as future open questions, on the unitary Schur sampling side, it would be, so first off, we expect the unitary Schur sampling algorithm to apply to be useful as a subroutine in any other algorithm that has this kind of permutation invariant input. So state tomography, cloning, spectrum estimation, etc. On the mixture sampling side, mixture sampling is still a fairly new concept. I think it was firstly presented at QIP last year. So there's not that many applications for the unitary mixture sampling. Schur duality can be used for some things, but as far as I know, there's no applications for a unitary mixture Secondly, it would be nice to have an efficient algorithm when the number of copies is smaller than the rank, or the dimension of the qubits. And on the set tomography side, well, we provided a sample optimal memory efficient algorithm. The last task to optimize is the time complexity, which unfortunately we were not able to do. And it would also be nice, as always, to obtain some lower bounds. This is always the hard part. Some lower bounds on quantum memory would also be ideal. And with that, thank you for listening. If there are any questions.
Very nice talk. So I have a question about the POVM step in the state tomography. So can you change the unitary, like hard random unitary to pseudo-random unitaries that was introduced this morning?
So pseudo-random unitary would probably be a little bit harder to analyze, right? A pseudo-random unitary gives you some indistinguishability property to the hard random unitaries.
Mm-hmm.
However, generally, it is hard to know what the distribution actually looks like. So my intuition is that it would be hard to characterize the outcome of this measurement, simply because you don't know the distribution. It would be possible maybe to look at like T or N designs. This is also something we considered, but that we couldn't quite get to in the end.
I see. Thank you.
Thank you for a very nice talk, and I have a question about your first part about the short sampling. So your the algorithm and the circuit you showed, it seems very similar with the swap test. So what's the difference between your circuit and swap test?
I'm not, off the top of my head, I'm not super familiar with the swap test circuit, but I think the swap test circuit basically just looks at the symmetric subspace between two registers. Here we
but you can generalize swap test. You can change the control swap gate into some like control permutation operations. Then you can project to any permutation invariant subspace you want, and it is also can also be done in a manner in a stream manner. So like what you show.
Okay, I was not aware of this.
Okay. Another question is about the second part in the application in the quantum tomography. So like you said, you can use some like random unitary to achieve the short sampling, and this part seems to be, to me, it's very similar with random measurement. You know, like you apply a random unitary on a quantum state and then perform measurement. Then you use this measurement data. You can construct some unbiased estimators for quantum state moment, and that protocol is also based on short-wave duality. So, like, what's the difference between your protocol and that kind of protocol?
I mean, I guess our protocol uses unitary Schur sampling as a primitive, and therefore we get the memory saving in the main part of the state tomography side is that we get the memory saving in like from 1 over epsilon squared to log of epsilon. But I'm not familiar with kind of the work that you cited, so I don't know in what other aspects they differ.
Okay, maybe we can discuss later. Thank you.
Yeah. So I have a question related to the first question. So like about in POVM on the state tomography. So like what kind of property for the subset is needed? Like is the approximate design enough, or do you require more properties?
So the subset that we used is simply generated through sequential queries to the Haar measure. When we were trying to optimize this so that it wouldn't have to be so large, we did look at T designs and N designs, and we couldn't quite make it work. I don't really remember the reason why.
Yeah, I think this way, like if you look at a T design, basically what happens here is if you kind of just choose it randomly, you don't need to take a smaller set because you just need to, you kind of need to be a T design, but just on every of the irreps. Whereas when you pick a T design, you would kind of, at least how, in the way that we worked it out, you would have to be a T design on all N inputs states, which is a much stronger requirement.
So it give you the efficient implementation that if you use the T-design.
No, this is not a T-design. This is like weaker than a T-design.
Yeah, right. But yeah, so that's the reason why you use a weaker. Yeah. Thanks.
Okay, maybe last question. Anyone? Okay, maybe I ask, do you know if you have also access to the complex conjugate state? You can get some advantage, and maybe, I don't know, mixed Schur sampling can be helpful for this, maybe?
For tomography? Or
yes, for tomography.
So I think it is known that state tomography algorithms with access to rho, the conjugate of rho, don't give you a significant advantage. I'm not entirely sure about the numbers, but it was not significant over the sample optimal algorithms, if I remember correctly.
Okay, thank you. Then let's thank again the speakers.